This is an e-lesson prepared by Henrique and Matthew, and it's about the Edmonds-Karp maximum flow algorithm. What is this algorithm used for? It is used for finding maximum flow in a network represented by a directed graph with weighted edges. This corresponds to some real-life problems such as finding the maximum possible bandwidth between two computers in a mesh network where packets can travel along any route independent of each other. Before we discuss the problem in more detail, we need to grasp the definitions of all the concepts involved. So, a network flow is a directed graph G equals the pair of V and E, where V is the set of vertices and E is the set of edges. And all of this has the following properties. Every edge in E has a non-negative real weight called the capacity of the edge. In the graph you also have one single vertex labeled S, which is the source, and one single vertex labeled T, which is the sink. The graph also satisfies the property that there is no edge pointing into S, so there's nothing flowing into the source, and there is no edge starting at T, which means there's nothing flowing out of the sink. Here I'll let you stare at the definitions for a second while I mention my original example of the mesh network. Imagine that every single edge represents a direct connection between two computers, represented by vertices, and that the edge weight is the max bandwidth of that connection. Now we represent the given flow across the network in an abstract way with a function that maps a pair of vertices, which is actually an edge, to a real value, which is the flow across the edge. The function inputs are an ordered pair, so it does matter which way around you put in the vertices, because if you put V and U the other way around to the definition below, you're going to get the value on the edge, which is going the other way round, so from V to U instead of U to V. Now you can see that the function has to satisfy certain constraints, which are, first of all, we require that the flow across any edge cannot be greater than that edge's capacity. And secondly, that all the flow that comes into a vertex has to leave. In other words, the vertex can't retain flow. Let me give you a non-abstract example. In our mesh computer network, if you couldn't get rid of data in real time, you'd have to buffer it. And if the situation carried on, you'd eventually run out of space. When we show flows on a graph, we're going to be using a slightly odd notation. Here you can see it. This means the flow is 8 out of a maximum capacity of 10 on this edge. Now the last definition before we formally state the problem. The value of the flow, as you can see, the notation resembles the way that we note the magnitudes of vectors, and the concept is actually quite similar. It's the measure of the total flow flowing from the source to the sink across the entire graph. And the way to obtain that value is to sum all the flow across the edges leaving the source. At the end of the video, you'll be able to find a link to the minimum cut maximum flow theorem, which shows that if you split the graph by any cut which separates the set of vertices into two partitions, where the first contains the source and some vertices, you'll be able to see how the capacities of all the edges connecting any vertex in one partition to a vertex in the other partition can determine an upper bound for the value of the flow. Now we are ready to state the problem formally. Maximum flow problems involve finding a feasible flow through a single source, single sink flow network that is maximum. The Edmonds-Karp algorithm is iterative, and it works by improving the result of the last iteration in order to obtain the optimum solution. For this reason, we introduce yet another concept of the residual network, which helps us to represent the intermediate results. Given a flow network G and our intermediate result, which is a flow, we can generate a residual network denoted G suffix F. Here are the rules for generating the residual network out of the original flow network and the given flow, G and F respectively. A simpler way to specify this would be to only apply the second rule with a slight modification where the less than signs are replaced by less or equal to signs, and then remove the zero valued edges from the residual network. This way the first and third rules become redundant. You can see on our example that for every edge in the original graph we add two edges to the residual network. One which is exactly the same except for the weight, and another which goes in the exact opposite direction. The edges have weights corresponding to what's left of the original capacity given the flow, and the given flow on that edge respectively. You should note that there are no zero-valued edges in the residual network. The idea of this algorithm is to keep finding paths from the source to the sink in the subsequent residual networks. I have to stress that the path always has to be the shortest path in terms of the number of edges involved. Otherwise, this is not the Edmonds-Karp algorithm. With each iteration, we push more flow from the source to the sink along the paths, and consequently increasing our flow continuously until it reaches its maximum value. The algorithm terminates when there is no longer a path from the source to the sink. So basically the whole thing is a bit like having a system of large drainage pipes of varying sizes and then trying to find the maximum flow by shoving garden hoses down different paths until you can't find a way to shove one more. The path along which we increase the flow in each iteration has a special name, the augmentation path, and here is an example. Each augmentation path has a residual capacity, which is the minimum of the capacities of the edges forming the augmentation path in the residual network. In this case, the residual capacity is equal to 2. Now we show how the algorithm works using an example. We start with an initial flow of 0, which results in a residual flow network, which is equal to G, the original network. Then we start iterating. We find any shortest path from S to T. In this example, on the first iteration, there are 4 possible choices. We arbitrarily pick the path that goes through A and D, and we augment. Now we have a flow which is 0 across all edges except the ones in our chosen path. And we note that the flow has completely exhausted the capacity of the edge from S to A, hence there is only an edge pointing backwards in the residual network, which we generate at the end of the iteration. In the next 2 iterations we can still take one of the shortest paths from the first iteration. Then things get a bit complicated because the 4th original shortest path doesn't exist anymore, so we augment along other longer paths. Just a quick note, this would not matter to a computer as it would perform a new path find at the start of every iteration. Most often the algorithm uses the breadth first search in order to find the shortest path to the sink. Now after 2 iterations with paths of length 6, the algorithm terminates because there are no more paths from the source to the sink. Here you can see that the maximum flow is equal to 14, which is given by the flow leaving the source or entering the sink. We can now derive the pseudocode. We start with a flow of 0 and that results in GF being equal to G. Then we need a loop for the iterative part. In each iteration we find the residual capacity and we augment the flow. The augmentation involves decreasing the weights of all the edges in the path by the residual capacity and incrementing the weights of all the edges pointing in the exact opposite direction along the exact same path, also by the residual capacity. When we can't find any more paths, we achieve the maximum flow, and we return the flow and its value. Now we show how to deal with special cases. If you have many sources or many sinks, you add the super source and the super sink, respectively. You add edges to the super source pointing to all the original sources, with capacities greater or equal to the sum of capacities of all the edges leaving each source as to not constrain the solution. Likewise in the case of the super sink, except that the direction of the edges is reversed. When you have 2 vertices with edges pointing in both directions, you add a virtual vertex in order to get rid of one of the edges. This also covers the case of an undirected edge, because in reality it's just 2 directed edges with the same capacities pointing in opposite directions. If you have a vertex with internal capacitance, which means that the total flow through the vertex is bounded, for example a bottleneck at a road junction, you split the vertex in 2 linked by one edge from the first to the second, where the former is pointed to by all the edges pointing to the original, and the latter has all the edges pointing out of the original pointing out from it instead. In order to discuss the time complexity of this algorithm, we need to state the lemma, which we give without proof. It basically states that with each iteration, the shortest path in the residual network from the source to any vertex which is not the source or the sink will increase monotonically, i.e. stay the same length or get longer. In every iteration of the algorithm, at least one edge in the residual network disappears, and it will be all the edges in the augmentation path which have their capacity equal to the residual capacity. From now on, we call such edges critical edges. I claim that for any edge, by the next time this edge becomes critical, the path length must increase by at least 2. Now we prove it. We see that the shortest path from the source to the vertex at the start of the critical edge, labeled U, is equal to the shortest path to its end, V, minus 1. This is because the critical edge is in the augmentation path, so no shorter path to V exists. And by the lemma previously stated, we said that in the next iteration the shortest path to U will increase monotonically. And the right side of the inequality equals the length of the shortest path from the source to V minus 2 because the edge is critical again. This way, every time any edge UV becomes critical, the distance from S to U is increased by 2. So any vertex U becomes unreachable from S if the shortest path from S to U equals the number of vertices in the graph minus 2. So if all edges become critical a number of times, so that every vertex is unreachable from S, the algorithm must have terminated. Then the number of iterations required for this has an upper bound in the order of V times E, and each iteration performs a shortest path search in the directed graph, for which you can use the BFS, which runs in big O E. Hence the total worst case runtime should be proportional to the number of edges squared times the number of vertices. There's our links to some further reading, which include the demonstrator and the Wikipedia page for maximum flow minimum cut theorem. Here are references which include the original lecture notes, a Wikipedia page, and a book about algorithms. The pseudocode was independently derived, and the diagrams in the work example were also newly created.